Welcome back, everyone. Now the next speaker to this plenary section is Claudianor Alves, professor at the Universidade Federal de Campina Grande. He is well known in his work, by his work in partial differential equations of the elliptic type. And I'm sure to say he is one of the finest in that area. So, and I am happy to tell you that Claudianor has got his PhD here in the University of Brasilia, so we are very proud of you. And having said that, Claudianor will talk to us about the existence and multipliers of normalized solution for some classes of elliptic problem. Thank you.
Okay, thank you very much, Matufu, by introduction. I am very happy to be here. Okay, all time that I came back to Brasilia, I feel very happy because as Matufu said, I made here my master in doctorate with Professor José Valdo, and I had here very happy moments. Okay, thank you for invitation. Thank you, Zu, for your attention and with me, okay? And today I will talk about the existence and multiplicity of normalized solution for some class of elliptic problems. And here I show for you the general problem. And we intend to find one solution of this elliptic equation, but in our case, our solution must satisfy one prescribed L2 norm, okay? And here, our potential V is one continuous function, and F is one continuous function, and these both functions, of course, will satisfy some technical conditions. Okay, in this talk, I will show for you some recent results that I wrote with some colleagues, okay? We have one paper with Xiaoji in your friend Olympio. We have another paper with Xiaoji from China and Olympio. Another paper with Xiaoji. I have one paper alone involving this type of subject. We have two papers with one colleague from Vietnam. And finally, another paper with Shen from China. Okay. First of all, I would like to talk a little bit what is the motivation to start this type of problem. And when did we study the existence of solution for nonlinear radial equation type 2, there is one important physical law that says that the mass of the trajectory is preserved. What this means? This means for us that study PDE, that the L2 norm is preserved, okay? I will try to draw here one picture. Okay. Of course, when we study the nonlinear Schrödinger equation, one famous type of solution is the standard wave solutions. Okay? It's one solution like that in blue. When you take this type of solution and you put here into and compute, okay, the calculus, you will see that this function u here must satisfy one elliptic equation like that. This here, okay? Okay, so this type of solution, normalized solution, okay? But before to continue my talk, it is necessary to say there is two types of problems. When you don't fix the L2 norm, you say that your problem is free mass. But when you fix the L2 norm, in general, the people call the prescript elliptic problem, okay? When the problem is free of mass, in general, you find a very rich literature involving this type of the situation. But recently, the problems involving the L2 norm prescribed is increasing, okay? Because in fact, we are learning how to get this type of solution, because it's not so simple, okay? Here, I show for you some important reference that show why the normalized solution is important in the physical point of view, okay? This is the reference here. Okay, one very important reference in this area is one famous paper due Casanave-Lyons. In these famous papers, the Casanave-Lyons, the authors studied the problem one that I showed for you a few minutes ago. Casanave-Lyons consider the existence of solution for this class of problem here by assuming that this nonlinearity is of one specific way, like power, okay? Here, absolute value of u power p minus 1 times u. And of course, they consider the potential V is equal to 0. What is the strategy used by that authors? The authors try to solve this minimization problem here, and in this famous problem, it was proved the following. If you consider the case where the problem is L2 supercritical, okay, and what is the L2 supercritical? L2 supercritical is when the power p is bigger than to 1 plus 4 over n, okay? This is the definition of the L2 supercritical. In this case, Casanave-Lyons showed that this minimization problem is not solved. In fact, they proved that this minimum, IA, is equal to minus infinity. But in the same paper, the authors also consider the case where the problem is L2 subcritical. L2 subcritical is the case where the power p lives between 1 and 1 plus 4 over n. In that case, Cazenave-Lyons showed that this minimization problem is solved. And in fact, that minimum is strictly negative for some a positive. What is the idea? The idea is the following. The authors prove that if you have one minimization sequence, it is possible to find one very nice translation of the minimization sequence, such that the translation of that minimization sequence is, of course, one other minimization sequence, but you can prove that the new minimization sequence is strongly convergent in H1. Of course, if you have one strong convergence in H1, you have in your hand one solution for your problem. Of course, okay, you are solving this minimization problem here, you will find one solution like this. And in your case, it's very important to say, because I forgot. When do you consider, I will use the picture here. In this problem here, this number lambda is unknown, because this number lambda is get by the Lagrange multiplier. Okay, this is a very delicate point, because when you are studying the Schrödinger equation with free mass, you can choose lambda. You can choose lambda of one convenient way, and when you try to find the standard wave solution, you can get one elliptic problem. In general, strongly definite that you can use the mountain pass theorem. It's the basic idea. But when you try to get the normalized solution, you don't know what is the value of lambda, because it appears as one Lagrange multiplier. Okay, after reading the paper do Cazenave-Lyons, I propose to my colleague Xiao Ji to consider the situation where in the left side of the equation appear one potential V. Because in the famous paper do Cazenave-Lyons, the potential V is equal to 0. What our goal? To understand what is the geometry on the potential V, such that we can prove the existence of a normalized solution. Okay? In that paper, we continue to study the L2 subcritical case like Cazenave-Lyons, and we prove that, in fact, there are 4 classes of potential that it is possible to find one normalized solution. You can consider the potential V periodic, asymptotic periodic. The potential V satisfies one geometric condition introduced by Rabinowitz, and the potential V can belong to one class of potential introduced by Barthes-Wang. For this class of potential, it is possible to prove the existence of normalized solution. What is the idea to prove? Of course, our inspiration is to follow the same strategy by Cazenave-Lyons, but of course, during this path, we find the challenge, okay, to get the solution. So our intention is to prove that the minimization problem for is solved. The idea is to consider that energy functional J, okay, and prove that this infimum is achieved. Okay. What is the first step? The first step is to understand what the relation between the infimum epsilon A with the parameter A. Of course, the parameter A is fixed, but it's very important to understand if I move the parameter A, the L2 norm, what happened with the infinite? In this case, we prove that this function, upsilon A over A squared, is one decreasing function. This information may be simple, but it is crucial to prove our one compactness condition. Here, I recall for you in all my talk, SA is this manifold here. This manifold is the L2 sphere intercept with the sublevy space H1. Okay, this is one manifold. Okay, it's not the L2. No, it's not one sphere. It's one sphere only L2. But in the sublevy space, we don't know what is the manifold. We prove the first compactness result. We were able to prove that if you have one minimized sequence, such that you know that the minimized sequence is weak convergence, you have the pointwise convergence, and you know that the weak limit is non-trivial, it is possible to prove that this minimized sequence is in fact one strongly convergent. It's a stronger sequence. This is a very important because, for example, if you know work with the elliptic problem invariant by translation, in general we use the Pierre-Lyon's result, and we prove in a lot of problems, elliptic PDE, that if you have a sequence and you have some problem with the weak limit, you change the sequence by translation and you get another sequence. This happened, for example, with minimized sequence, PS sequence, and so on. So here we say, if you get one minimized sequence, just that we know that weak limit is non-trivial, I am able to prove the strongly convergence. So with this information in your hand, we prove the existence of normalized solution for that class of potential V. After, okay, I go for one alone project. In this paper that I wrote alone, my intention was to prove the existence of multiple normalized solution. Because in the literature, there are many papers, or not many papers, but some papers that prove the existence of multiple normalized solution, but the authors assume, in the most part of them, that the nonlinearity is homogeneous, that is, f does not depend on x, or when f depends on x, they assume that f is radial with the variable x, because in that paper, the authors works on the H1 of the radial functions. Because when you work there, you get very nice compact embedding. Okay? And here, my goal is I want to work with one class of problems that the nonlinearity is not radial in the variable x. It is possible now to find multiple solutions. Here, we prove that. The motivation, of course, this comes from one paper due at Cal, where Cal proved that the geometry of the function h that appear in the right side of the PDE is strongly related with the number of solutions of one PDE, elliptic PDE, with free mass. Cal proved that the number of solutions is at least the number of maximum of the function A. Once that I know that result, I ask for myself, it is possible to get the same result here? The situation is totally different, because in the paper to account, the geometry that they work is the mountain pass geometry. Here, no. Here is one minimization geometry. It's totally different. It is necessary, in fact, develop one new strategy to solve the problem. So, here, in this paper, we consider one large class of nonlinearity. Okay, one large class of nonlinearity. In the most part of the paper, the author assumed that the nonlinearity is homogeneous, like this. Here, I try to avoid this type of property. So, in fact, we proved that when epsilon is small enough, the number of normalized solutions is strongly related with the number of the maximum of the function A. Okay? What is the idea? The idea is to, again, consider the minimization problem involving the problem that you want to solve. And if you have some experience with this type of problem, you know that the autonomous problem is very important. It is necessary to understand in details what happened with the autonomous problem, okay? So here, we prove one very, very important result. We prove that if you consider the autonomous problem like this, I recall for you that the famous paper do Cazenave-Lyons consider one specific case. And they prove that, in that case, if you have one minimized sequence, they prove that it's possible to translate to get a new sequence, and the problem is solved. Here, we prove that behind the famous paper do Cazenave-Lyons, there is more information. And we prove this compact result. We prove that, in fact, you can work with a large class of nonlinearity, and you can prove the same result that Cazenave-Lyons proved in that paper. Okay? Using this information, we go to the next step. What's the next step? The next step is the following. Here, we don't have in your hand the symmetry to help us to get some estimate. So, it is necessary to understand, if you don't have one strongly convergent, what we lost? So, here, we prove the following. If you have one PS sequence on the manifold SA, if you don't have strongly convergent, it is possible to find one number beta, such that this number beta does not depend on epsilon when epsilon is small enough, such that the L2 norm, okay, is bounded from below by that constant. That constant say for us what we lost in the L2 norm when the strongly convergence does not happen. This is a very important. This is one key point in your paper. After this key lemma, I was able with my colleagues to solve more difficult problems. Okay? This lemma is key, é key lemma, because this lemma, together with the compact result, permit to prove, in fact, the PS condition for your functional at some levels. Okay? And here, of course, I will avoid details. My intention here is not to show details. If you like this subject, you can find in archive, you can write for me, and I can send for you the preprint, or some of them are published. Okay, after this paper, I went to another problem, with Thin. And now our intention is to following. We don't consider here F depend on X. But we come back to work with here in the left side with one potential, V. Here, again, we work with the geometry introduced by Rabinovitz. In this moment, it's very important to recall that when you try to find the standard wave solution for free mass, there is one famous paper by Rabinovitz that Rabinovitz proved. For the case of the mass is free, it is possible to find one solution for Schrödinger equation when epsilon is small enough. What is the challenge here? It is possible to prove the same result by Rabinovitz by this class of solution. Of course, in the famous paper by Rabinovitz, the geometry is totally different, because there Rabinovitz used the properties of the mountain pass level, and using the property of the mountain pass level, in particular the properties of the Néhard manifolds, it is possible to understand the behavior of the mountain pass level with relation to parameter epsilon to prove, in fact, the existence of solution when epsilon is small enough. But here, we lose the mountain pass geometry. We are working with the minimization problem. How to do that? Here, again, we need to introduce new ideas, and in fact, okay, it was necessary to understand. Oh, of course, sorry. In the paper of Rabinovitz showed only the existence of a solution. After, in one paper that I wrote with Giovanni Figueiredo, that working here now, we proved that the geometry of the graph is very important, because if the points, the set of the points where the potential V achieve the minimum, if this set is topologically rich, it is possible to prove the existence of multiple solutions associated with the category of the Lewis-Nick-theorem. We together these ideas, and we proved that in this case, it is possible to prove the existence of multiple normalized solution using, again, the category of the Lewis-Nick-theorem. Okay, and here, when epsilon is small enough, this is our main result. Okay, of course, here the potential V has one technical restriction here. For me, it's not so strong, because it's associated with the technique that we are using to show our solutions. And here, in some sense, we show again the concentration phenomena involving the maximum point of our normalized solutions. What is the idea? The idea, of course, motivated by the study made for the mountain pass level, we, in your case, so that this number here is one infimum, but in your case, it works like the mountain pass level. It was possible to prove that if we understand in details the behavior of this number epsilon, okay, we prove the same case. Of course, note that, for example, the mountain pass level is positive number. Here, our level, all of them are negative, all of them. So some estimate is not clear that happened, okay? So we begin our study to try to understand what is the relation involving the infimum that we need to solve with the autonomous case. Here we have one similar result involving the sequence, But here, I ask your pay attention, because here in this lemma, we don't have necessarily one minimizing sequence, but here one general sequence. The key lemma, using the key lemma, we prove this, okay? In this type of problem is a very interesting, because, for example, in that paper that I proved the multiple solution by using the graph of the function 8, what is the strategy to prove that the solutions are different? You choose in the manifold SA sets where the barycenter of this function here is close to the maximum of the function A. And you minimize locally in this set. And by using echelon, you prove that it is possible to find one local minimum in all that regions, and you, of course, can conclude that solutions are different, okay? Here is the same, but we use the barycenter technique to relate the manifold that you are work as A with the set involving the minimal point of the potential V. Here, okay, we are following all paper that work with the free case, okay? Oh, I look for one free case problem and I ask me, it is possible or no to get the same type of solution? Of course, there are a lot of that I don't know at the moment, if it's possible or no, okay? So I invited you, if you like this, I am here to work with you about involving this subject. When you see in the literature, there is one famous paper due the opinion family. The famous paper the opinion family is after the paper due Rabinovitz. Rabinovitz studied the situation where the potential V has this type of geometry. Okay? Here, in your case, V can be 0. In the Rabinovitz case, V has influence strictly positive. This is the geometry doing Rabinovitz. And the geometry introduced by the opinion family, they work with the local case. The local case generalize this geometry, because in the local case, the authors only assume that there is one region lambda, such that the potential V has locally this type of geometry. Okay? So, this potential can have this geometry at infinity, totally different of the Rabinovitz geometry. Okay. In this paper, famous paper, the opinion film showed the existence of solution when epsilon is small enough. After, I wrote one paper with Giovanni and proved that, in fact, in that paper, there are more solutions, because the graph, the region on the potential V achieve the minimum. If this region is topologically rich, the number of solutions depends on the category of the set. Okay? So we get all this information and try to solve this. And we got the same result. We proved the existence of multiple normalized solutions, and the number of solutions is at least the category of the set where the potential V achieve it's minimum. Okay? This is one preprint. Okay? We are waiting for answer of the journal. But here, I would like to point out what is the big problem here. In this paper due the N.V Thin, the authors, when they work with the free problem, the N.V Thin introduced one penalizing method. What is the penalizing method? The penalizing method is essentially the following. They consider one new function, phi tilde, and they consider phi tilde like this, ft, t less than or p, and here you put b0 of k, t bigger than or p, and fp of course equal to b0 of k to become this function continuous. So they consider one new nonlinearity like this. And they propose one new elliptic problem involving this nonlinearity, and they prove that when f is small enough, there is one solution for the new problem. But what is the idea? It is necessary to prove some estimate involving the L infinite norm of calculate the L infinite norm in this, the complementary of the set lambda is less than of e, because when this happens, you get the original problem. We prove that the solution of the new problem is in fact one solution. But here, this term does not work well. We spend a lot of time to find what is the best penalization that we need to use here. And for my surprising, it's that. It's not more one linear perturbation. Because in here, we have one linear perturbation. For the normalized situation, no. You need to put that way. Okay? So, with this information, new estimate appear, and we prove that it was able to prove the estimate and so on. Okay? But I would like to talk a little bit. Matofu, how my time? Okay. I would like to talk a little bit about the L2 supercritical case. This is a very important problem because I talked a few moments ago about the famous paper do Cazenave-Lyons. Cazenave-Lyons proved that the minimization problem is not solved. But the fact that the minimization problem is not solved does not say that there is no normalized solution for L2 supercritical case. Only say that this approach is not good to get the normalized solution. Okay? After 30 years, okay, Jian write one very interesting paper involving the L2 supercritical problem, and Jian teach how to work with this situation, and Jian show for us that it's possible to work with the mountain pass geometry on the manifold SA and prove the existence of a solution. Of course, it's a very interesting because in this manifold, we don't know if this manifold is planned. Because when you are working with the Sobolev space H1, you can work, for example, in lines. But here, no. It is necessary to understand what is the good path that you need to use in the mountain path geometry to get your solution. Okay? And here, Jan shows for us, there is one rescaling that works well, and that rescaling works like the path that we need to use in the mountain path geometry. This is a very interesting point. And here, okay, we have one beautiful, beautiful paper, okay? After the paper do Jan, okay, I work with Olympio and Xiaoji, one paper here. But, of course, there are very, very interesting papers in this subject. I say that the Jan is the papa of this subject, because it's a very interesting, the very good paper that he has involved in this subject. Sometimes I write the paper and send him. I ask Jan, what is your opinion? It's good or no? Okay, but it's a very good guy. In this paper that I wrote with Xiaoji and Olympio involving the supercritical case, okay, our main contribution was the following. We observed in the literature there is no result involving the normalized solution involving, for example, in dimension 2, the nonlinearity with the exponential critical group. And we decided to find this situation, and in fact, we proved that there is normalized solution. This is the first paper involving normalized solution and the exponential critical group. For dimension n bigger than or equal to 3, we work with that situation, but there was in the literature some papers do Nicola solve. Okay? It's very important to say that there are papers involving the multiple normalized solution for the L2 supercritical case, and in this case, the genus theory is the main tool used. Okay? Here, I show for you some papers involving the multiplicity normalized solution, and we have another paper with Olympio. Olympio works a lot, and we have this paper here. And Xiaoji will visit Olympio next July, okay? I think that we will write 10 papers involving this subject. And here we have our contribution here. Our contribution of the multiplicity, of course, because when you consider the critical exponential group, how we prove the multiplicity of solution, because in the literature there is no similar result. And then here we introduce one new way to get the multiple normalized solutions. Okay, we are working to finish it because it's closer to have lunch. Now, one very important question. Look, in all my talk, I mentioned papers in Rn. What happened when the domain is bounded? Okay? If you consider one bounded domain, the L2 subcritical case is a homework for my student in Campina Grande. It's homework, because you have a bounded domain, you have a very nice compact embed, and you solve. It's not difficult. But the challenge is to work with the situation L2 supercritical. Because I tell you a few minutes ago that Jian shows for us that there is one high scaling that is possible to work in a lot of problems involving the normalized solution in H1, but that high scaling move the bounding domain. When you try to use the high scaling, it's the domain is not invariant. When the domain is bounded, it's not invariant by that high scale. So I only know 4 papers involving bounding domain. 4 papers. Papers do Benedetta Pelati, né? E tem 2 guys, tem Hugo Tavares. But the main point is, when the domain is bounded, the framework is totally different. In general, the Mohs index is used there. In these papers involving bounded domain, right now, I am not able to understand. The technicality is totally different. It's very hard, okay? But I am from Brazil, and I don't give up. Once that I didn't understand, I create my new method to find one solution, okay? And here, in this paper with Shen, we introduce one new way to find normalized solution for bounded domain that does not use Mohs index and the uniqueness of solution in Rn. Because in some of papers, the authors, in some sense, project the solutions of this problem here. It is well known in the literature that this elliptic PDE has uniqueness of solution, at least translation, okay? The authors take one solution of this problem and make one cutoff of this solution and try to find the normalized solution using this cutoff of this part of the solution. It's the computation, it's so hard. It's very difficult for me, regular person, okay? So, but here, okay, it's here I cite the Norris, Tavares, Vecini, okay? This is only this paper here involving this type. I send to Jian this. In one recent paper, do Jian, they cite our method has one provisional method in this type of solution. Okay, I believe that. I will finish here. Thank you very much for your attention.
Well, thank you, Graduate Claudianor. Very nice talk and wonderful survey on the subject. Now I will ask the audience if there is some remarks, comments, or questions. I think this subject is too difficult. Oh, Olympio, please.
First of all, Claudianor, congratulations Beautiful talk. Showing good
You are my
teacher
friend.
also.
You are my friend.
Claudianor, can you tell for us what happened for L2? Critical number problem involving critical.
No, the situation L2, because
Yeah.
there is the classification of this problem are in three classes. The L2 supercritical, P bigger than 1 plus 4 over n. L2 subcritical, P less than 1 plus 4 over n. But there is the critical case. P is equal to 1 plus 4 over n. The situation critical, in general, you prove the existence of normalized solution when the mass is small. It is possible to recover because the L2 supercritical, there is one competition involving the power of the gradient. Okay, it's 2 in the right side. When you take make the computation, it's the same order, because here one very important inequality is do a Nuremberg. How can I say? Do you recall the famous inequality? It's the inequality that you can prove that the LP norm is less than the one constant, L2 norm, 1 power, the gradient norm. Nuremberg. Thank you. Okay. When you work with the L2 supercritical case, when you use this, there is one computation. In order to overcome the difficulty, you assume that the L2 norm is small, and you can work again. Okay.
Any other remark? Questions? Oh, Márcio.
Yeah, you know, I don't know all techniques. So in the previous problem, when you have 1v times u, the question is just a curiosity. Are there researchers that put the lambda u in the other side, and then write v minus lambda u, and then give you some assumptions on v in terms of lambda, or not? Just a curiosity.
You are talking about this?
Yeah, exactly. When you add v, instead of giving several other assumptions on v, capital V, then you put on the right. Yeah, you can put it on there, and then you're going to have lambda minus v, and then assumptions.
Okay. It's the situation, for example, when you assume that potential V change signal, or for example, when the potential V is negative. If the potential V is negative, you can rewrite here V as minus V, and you put in the right side. It is possible, okay? It is possible to consider here. In my previous paper, I didn't work with this situation, but right now, I'm sure you can consider the potential V negative once that the L infinite norm is small enough. Now I know the trick to make the machine works well. Okay?
Any other remarks? Comments? I have a comment.
Okay.
When we can have the pleasure to see your new methods for bounded domain?
Yes. In fact, after some months reading the paper, I saw that in all that paper, when the domain is bounded, the mass need to be small. Okay? So I observed that in the normalized solution, if you assume that the mass is small, it is possible to prove that there is one region in the Sobolev space that the normalized solution must live there. So I propose one new truncation, and we work with a new problem, and we prove the existence of normalized solution for that new problem. But in fact, that normalized solution lives in the region that the normalized solution of the original problem works, and after some computation, we proved that the normalized solution for the new problem is in fact the original problem. There is one truncation behind the argument. Okay, but it still hold for A is small enough, okay, when the norm, L2 norm is small. Because in the first moment, I have a doubt if the R result is good because we assume that the L2 norm is small. But in the literature, all that paper are published in calculus of variation, JDE, and so on. I believe that. If that are there,
It's
I
quite
suppose
interesting.
that the referee don't criticize the fact that in your case the L2 norm is small. I hope.
Okay, let's thank again Professor Claudianor. Outstanding conference.